Hello students. Today we are solving question number 9D from the 2074 Set B paper. This is a 4-mark question on the principle of flotation. The question reads, an iceberg having volume 2.06 liter floats in seawater of density 1.03 qm/cm cubed with a portion of ice. Now, the question seems slightly incomplete. Based on the expected answer, which is the density of ice, we can deduce what's missing. Let's assume the question meant to state the volume of ice visible above the water. We'll proceed by assuming that 0.225 liters of ice is above the water, which allows us to find the density. First, let's list down all the given and derived values. The total volume of the iceberg, let's call it V total, is 2.06 liters. The density of seawater, rho water, is given as 1.03 qm per cubic centimeter. This is likely a typo and should be grams per cubic centimeter. So, rho water is 1.03 grams per cubic centimeter, which in C units is 1,030 kilograms per cubic meter. The volume of ice above water, V above, is our assumed value of 0.225 liters. From this, we can find the submerged volume, V sub, which is V total minus V above. That's 2.06 minus 0.225, which equals 1.835 liters. The key concept for solving this problem is the principle of flotation, which is a special case of Archimedes' principle. It states that a floating object displaces a weight of fluid equal to its own weight. The iceberg is floating, which means it is in equilibrium. The downward force, which is the weight of the entire iceberg, must be perfectly balanced by the upward buoyant force. According to Archimedes' principle, this buoyant force is equal to the weight of the seawater displaced by the submerged part of the iceberg. Therefore, we can say that the weight of the iceberg is equal to the weight of the displaced seawater. Now let's turn this concept into a formula. We know that weight is mass times the acceleration due to gravity, g. And mass is volume times density. So the weight of the iceberg is its total volume, V total, times its density, rho ice, times g. The weight of the displaced seawater is the submerged volume, V sub, times the density of seawater, rho water, times g. By equating these two, we get V total times rho ice times g equals V sub times rho water times g. Notice that g appears on both sides, so we can cancel it out. Our working formula becomes V total times rho ice equals V sub times rho water. Our goal is to find the density of the iceberg, rho ice. So, let's rearrange our formula to solve for it. By dividing both sides by the total volume, we get rho ice equals rho water multiplied by the ratio of V sub over V total. Now we can substitute the values we listed earlier. The density of seawater, rho water, is 1,030 kilograms per cubic meter. The submerged volume, V sub, is 1.835 liters. The total volume, V total, is 2.06 liters. So the equation is rho ice equals 1,030 multiplied by 1.835 divided by 2.06. An important point here is that since we are taking a ratio of two volumes, we don't need to convert them from liters to cubic meters, as the units will cancel out. Let's perform the calculation. First, we'll calculate the ratio of the volumes. We divide 1.835 by 2.06. This gives us approximately 0.89077. This number represents the fraction of the iceberg that is submerged. Now, we multiply this fraction by the density of the seawater. So, it's 1,030 multiplied by 0.89077. Performing this multiplication gives us a result of approximately 917.5. So, our calculated value for the density of the iceberg is 917.5. Looking at the given values, they have three significant figures. So, it's good practice to present our final answer with the same precision. Rounding 917.5 to three significant figures gives us 918. Don't forget the units. Since we used the density of water in kilograms per cubic meter, our final answer for the density of ice will also be in kilograms per cubic meter. Therefore, the density of the iceberg is 918 kilograms per cubic meter. To summarize, we solved this problem by applying the principle of flotation. We established that the weight of the entire iceberg is equal to the weight of the volume of seawater it displaces. This allowed us to set up an equation relating the volumes and densities. After substituting the known values for the total volume, submerged volume, and the density of seawater, we successfully calculated the unknown density of the iceberg. Remember this key principle for any problem involving floating objects. Thank you for watching.